Today what we're going to look at is what we call tolerance stackup. Now, assuming that we know something about individual tolerances, tolerance stackup addresses the issue. For instance, if we look at this little drawing here, we have a lot of little components that are going into this building, and each one of those could have a tolerance. And the question here is, how do all these effects add up to our final product? So that's what we'll be looking at today. First of all, given that we have the potential for multiple features, we would have multiple dimensions, and those dimensions could have tolerances that are interrelated. And that's what we're referring to as tolerance stackup, and they end up affecting the overall features of the product. What's the relationship of this stackup condition to the type of dimensioning that we saw last time? And what's the relationship to manufacturing? What's our connection here, and why should we be concerned about that, given that our focus is on developing a manufacturing system? We'll see certain effects on the fabrication processes and assembly processes that we use in our manufacturing system. Well, if we take a look at it from our manufacturing perspective, what we're going to see is that there are certain sources of variation in manufacturing. And those sources have to do with certain aspects that you're going to design into your system. For instance, you're going to have a set of tooling. And the tooling is used, and we'll see later on when we get into the tooling aspect, to perhaps locate a surface using a fixture. And you've done that in the lab, and you know that you can put a part with respect to a specific machine, but there could be variation in locating that part on a surface in the fixture. There could also be variation when I place that tooling, that fixture, on a machine. So every time I do a setup and add it to the machine, it could be in a different location. And then, of course, we've got tooling that comes in contact with material. And when that happens, you know from IE 248 that tool wear can occur. And if tool wear occurs, then we know that has a direct effect on our dimensions. Material. So we have stock material that we order. And when I examine that material, you know from material science that material is not uniform. So if the material is not uniform, then the properties of that material will also not be uniform, and therefore it will behave in different ways in different regions, having an ultimate effect on the dimensions of our product. Or we might have internal stresses in the material, and once we remove certain areas, that internal stress could be relieved, causing dimensional changes. And then, of course, we can just have variation of surfaces from previous processes that affect the next processes. Now, here's probably the biggest source of variation that we're going to see in our system, and that is the operator. And the operator, being human, is going to introduce the most variation into our system. Why is that? Well, some examples might be inconsistent setups when I place that product on a specific process or machine, or maybe I'm manually controlling the process, and every time I do that, it will be slightly different. And if I get a different operator, of course, it will be different as well. If we look at the equipment that the operator is using, we note that there's a certain repeatability of motions. Every piece of equipment is going to have constraints in terms of how well it will be able to repeat a specific motion. And we'll see that later on when we get to the equipment aspect. If I look at the machine elements, so this machine has been designed to accomplish a certain task. However, parts of the machine have been assumed to be completely rigid, and that, in fact, is not true. And various components are going to twist and are going to bend. They're going to expand and contract with temperature, and so that causes dimensional variation if we're using that piece of equipment to produce a part surface. And then, of course, we could have some variation in parameter settings. So you know from 248, you set the feed rate, so how fast the table is moving, and the spindle speed, how fast the spindle is rotating with the tool. And that speed will not be constant, so there will be some variation in that speed. Every time I set it, it will be slightly different, and the feed rate as well. Then, of course, we've got an environment, and manufacturing systems are typically not in well-controlled environments except for specialty products. So we tend to see huge temperature variations depending on the location and the environment around it. And we know from our physics that temperature variations affect the material. So the product itself, if the temperature goes up, will expand. Temperature goes down, it contracts, and then we place it into a work envelope with tooling, and that is also expanding and contracting. So we get this compound variation. We could also have effects due to humidity. Depending on the nature of the material, humidity may cause different aspects of the product to expand or contract or cause problems for a process. This is not an exhaustive list, but it gives you an idea of what you should be thinking about as we go through this course. What is the net impact of my manufacturing system on dimensional variation that I'm going to see in my product? Again, that will affect your ability to achieve the level of control you want in terms of meeting your tolerances. So what could we do to, if we think about strategies to reduce this cumulative effect, what can we do to alleviate that or remediate that? Well, one thing we might want to think about is in our setups that we're going to be dealing with, what we like to do is minimize those. Anytime I can minimize those, that will help me minimize variation. Or I could spend more money on process controls. So this is a cost issue. If I have tighter controls, then I should be able to reduce the variation. Or I could introduce environmental controls in the facility. Now, depending on how large this facility is, this could be quite costly. Or there may just be certain aspects of the facility in terms of specific processes that we might want to control in terms of its environment, and therefore the cost would be reduced. Or we could think about going to a different vendor for our material. If we're not getting the quality material that we need in terms of uniformity, then we might try to find another source. Of course, anything we can do to reduce variability with the operators would be a good thing. Some of that can be done with training. Other things could be taking the operator out of the loop. In other words, trying to remove them by introducing equipment and or tooling that essentially reduces the variation that was introduced by the operator. Well, what does the Stackup look like? Let's take a look at an example here. And in this example, we see essentially three features on the part, and we're just looking at it in 2D for right now for simplicity. And what we're looking at is some cumulative effect of deviations. As we know, deviations are occurring as a result of our process, and those deviations are going to affect this overall dimension that I have as a question mark. What we're trying to do from the designer's perspective is control individual features here, as we can see, and you should be able to identify at this point what type of tolerance this is in terms of dimensional tolerance. If that's fuzzy, you need to go back and review the previous lecture. What are the implications of these multiple tolerance specifications? Well, we can think of it as an individual feature. Now, if I look at this overall length as some type of feature because this is going to fit into some subassembly, then I would be concerned about what that's going to look like after I produce a product. And, of course, any relationship to other parts that are going into assembly. For instance, if we have a part that's mating up against that surface or this surface, then we would be concerned about just those part features. But if we're looking at something overall, then I'm concerned about this question mark. Now note the question mark, that's not specified in the design. So we're not talking about going back and modifying the design per se. What we're talking about is from a manufacturing perspective, we're trying to understand this variability so we can prevent any problems down the line. Well, one way to estimate that, in other words, it's not specified, so we have to come up with some estimate of it. What we can look at is this worst case scenario. So in this worst case scenario, we'll go back to this concept of maximum material condition and least material condition for the part features at the boundaries. And what we'll do is either add or subtract, depending on the nature of the feature, and determine what's the worst case scenario here for the locations of these surfaces. Note that I might be concerned about that because I'm creating a fixture for this part, and therefore I would be concerned about where it's located with respect to other features. A different approach would be, let's look at it from a statistical point of view. So I know that 231 was a favorite course of yours. If you go back and look and review Stat 231, you can think of an independent random variable corresponding to that surface, and its location will vary from part to part. If we equate the tolerance, which is typical, to some interval of a probability distribution, and usually that is a 6 sigma range, and we'll see that later on as well, then all we have to do is add up the variances and determine the interval that is the cumulative effect of the individual part features, and we'll look at an example of that. So let's look at this worst case scenario. That's pretty simple to do. Here, as you recognize, we have chain dimensioning. And in chain dimensioning, I essentially have links that are interrelated, as you can see here. And here is my chain. So all I have to do is find the minimum and maximum, again corresponding to least material condition, maximum material condition. So as you can see at the top here, I have the largest dimensions. So 2.5 would be the largest here, 3.2 largest here, and 2.5 largest here. So overall, this is the largest the part can be, given that these three features are within their specifications. And then we just do the opposite. We use the smallest value and come up with the smallest possible overall dimension. Based on this simple worst case scenario, we're expecting that part to be somewhere between 7.8 and 8.2 in its overall dimension. Note, this is not, let me just emphasize that, not a design specification. This is something we're doing after we've received the design specification to get an understanding of this overall variation. So that's the worst case scenario. That's pretty simple. Now if we look at the statistical approach to that, we can use the same example. What's going to be different here is that we're going to look at it from this random variable point of view. Now when we make that assumption that we have independent random variables, you know that what we're really saying is that the features are created independent of each other. Now that may or may not be true, but that's the assumption that we're going to make. So you have to think about whether or not you're violating that assumption and how that might affect it. In other words, it could reduce or increase the overall variance, most likely decrease them. If they're independent, you should recognize that if I have n random variables, all I have to do is add up the variances of each one because we're treating them independently. Otherwise, we'd have to take into account the covariance. So now what I have to do is determine, well, what's the variance of each one of these features here? In order to determine that, I'm going to look at this range and say that this range is equal to 6 sigma, this range is equal to 6 sigma, and so forth. So each one of these has a sigma. We could call it sigma 1, sigma 2, sigma 3. And so each one of them represents a 6 sigma range, but these sigma 1, sigma 2, and sigma 3 are not equivalent. What we're going to end up with is a distribution about 8. And where do I come up with 8? Well, if I look at 8, 8 would be essentially the midpoint based upon the individual features, right? And I'll let you go ahead and calculate that yourself to verify that that is indeed true. If I take that midpoint or mean, I will have plus or minus 3 sigma total. So this is our unknown. This is what we're trying to find. Well, it's pretty simple. All we have to do is add up the individual variances. So this shows an example of how we would work that out. If, for instance, this, if you recall, this is sigma 1. So if I take 6 sigma 1, this range here, and equate that to our value, then 6 sigma 1 is 0.1. And then, of course, simple algebra, we solve for sigma 1. And then we do the same thing for sigma 2, end up with 0.2 divided by 6. And then, of course, we don't have to solve for sigma 3 because the difference is the same, so it's the same value. Now we're going to square them, add them all up, and come up with our result for 3 sigma. Note here I've replaced sigma with an S, indicating that this is really just an estimate, and it's probably not the true variance. So then when we solve for our sigma squared total, we just square everything, add it up, and now we come up with our variance. Take the square root of that times 3, and we end up with 0.125. So it's 8 plus 0.125, 8 minus 0.125. Note here that our value is significantly different than the worst case scenario, hence the term worst case scenario. So with a statistical point of view, this is really what we're expecting. And if we have a normal distribution, then you know that 6 sigma, that range that we're dealing with here, is a large percentage of all the products that we produce. So this is kind of our expectation of where these surfaces will be with respect to each other. And it's much tighter than the worst case scenario. So this would allow us to essentially accommodate that type of variation in a smaller range. Now, if I look at baseline dimensioning, where we're using one reference surface to determine the other part surfaces, so we see a distinct difference here. Everything is based, in this case, upon that surface. And now the question mark is not the overall dimension, but the designer's concern was these surfaces with respect to this surface here, right? But we might be concerned about how wide this part feature is because we might be using it in a fixture or some other aspect of the process. So now we have a slightly different tolerance stack-up condition here. And here we note that, first of all, this has no effect on the tolerance stack-up. So that's one of the first things that you really have to determine when you're tolerance stack-up, and that is what are the features that are involved in this condition and how do they ultimately affect that part feature that I'm looking at. So really all we have to do is concern ourselves with these two features, and in this case we can see we're subtracting to get the difference, and if that's true then it's going to be slightly different when we go to our worst case scenario. So let's take a look at that. In this worst case scenario, now we're going to take the largest distance, again with respect to our baseline here, and that will be our 5.7. That's how far this surface will be from that surface. And then we'll take the smallest distance, so we're essentially saying how far can this surface move in that direction, because we want to find the widest that this part can be, 3.3, with respect to those two surfaces. So whether you add or subtract will depend on the relationship between the features. So you can't just blindly add or subtract these numbers. You have to see what the relationship is to get the largest and smallest dimension. And then, of course, to get the smallest, we're going to move that surface in that direction, the surface in this direction. So it will be the smallest dimension for that feature and the largest dimension for this surface here. So we end up with 3.0. And now we're expecting our part feature to be in that range. Of course, we can go and look at the statistical perspective of that as well. Again, I don't have to worry about this feature here. All I have to do is concern myself with these two surfaces, and now n in this case will equal 2. I'll have a sigma 1, which will just be the variation in those two, and sigma 2 here, the variation in those, add those up, that is going to be my total variation. Of course, what would be the midpoint? Again, that's based upon our range here. And you can go ahead and calculate that for yourself, but you can see I'm just taking the mid-range of those dimensions. So when we calculate that, as we would expect in our statistical approach, my 3 sigma is 0.114, so this range is significantly less than what we saw in the worst case scenario. So at this stage you should be able to recognize how to determine tolerance stack-up based upon the relationship between features, both in the worst case scenario as well as the statistical approach. Now, what happens when we have an assembly? So that was tolerance stack-up in an individual part feature. But in many cases, we're joining parts together to form an assembly and or a weldment where we're actually welding the parts together. So the question is, how does that relate to our overall dimensions? Well, it's the same type of approach. First of all, we could have a very simple case of a linear stack-up, similar to that first slide with the bricks or the stones on top of each other. If I add a sequence of parts together, then my overall tolerance stack-up will be just as we did before. It'll essentially be the sum of the individual components, whether it's worst case scenario or a statistical point of view. So it's really proportional to the number of parts. And that's something you should really think about in terms of evaluating the product that you're producing. How many parts do I have, and how do they contribute to the overall stack up? Because again, it's cumulative, and it's going to have an impact as you produce this product throughout your system. Now that's a very simple scenario, the linear stack up. But we could also have nonlinear type of effects, because when I put my product together, it's not necessarily a 2D product, but it's three-dimensional, and I could have multiple surfaces making contact such that different surfaces influence the total stack up. And that affects the seating of a surface, and it could be affected by fasteners in that assembly. So here I've got my part here, and the question is, if I were to enclose that part in another part, oops, so if I were to enclose this part in another part and then in another part, then the question is, what would this overall dimension be? And at this stage, you should be able to, if it's a simple linear stack, you should be able to calculate that based upon worst case scenario or the statistical approach. But what happens when I've got a part that comes in contact with multiple surfaces, multiple part features, and it may not be fully seated against that surface? And so in that case, I might have some type of nonlinear effect. For instance, I could be coming up against this surface or that surface, or in fact, any of these surfaces. And one or more of them could be contributing to that. So things can get a little complicated. What do we do in that scenario? Well, in many cases, we turn to computer models where we will essentially simulate this assembly so that we can predict the overall variation in this dimension here. So it may be difficult to calculate that worst case scenario or statistical directly, but with our computer model, we can generate estimates of those that are fairly accurate. So based on what we've covered up to this point, you should understand the effects, the potential effects of accumulating tolerances. Fundamentally, it's going to increase the variation overall. And we saw different effects depending upon whether we're doing chain dimensioning or baseline dimensioning. And you should be able to cover either one of those. And our total variation is based upon individual feature variation. So keep that in mind as you develop your manufacturing system. What you're worried about is, as I create variation in the product due to these deviations in individual part features, they are going to contribute to the overall variation. And as we accumulate these, if I have a lot of different parts that are put together and a lot of different part features, then I can have a very significant variation in our final product. So in summary here, you're focused on features. Features are what we're producing in our individual processes, and those overall variation can be affected by individual tolerances that we have on other features, in other words, coming from the design spec. If I look at chain dimensioning, then we're focusing on individual features, and we saw that in the example. If we're using baseline dimensioning, then we're thinking about relating features to a common reference surface. Again, we're trying to tie features together so there's more of a connection between them, versus chain dimensioning, more independent view of the features. Tolerance stack-up occurs when geometry is dependent on other features, and we saw that as we looked at the overall dimension of that simple part. And the actual deviation, of course, is based upon all the processes that you are using in your system. So one or more processes could be affecting those individual dimensions, and therefore the tolerance